In this video, I'm going to use Wolfram-Cloud or Mathematica to explore a little bit more a problem I've looked at before, the perfect shuffling problem. Um, so you have a deck of cards or some list or array representing the deck of cards. You split it up into two piles and you sort of interleave it, taking the first card from the first pile and the first card from the second pile, and then the second card from the first pile and the second card from the second pile, and so on, and create sort of this new rearranged array. This is also known as riffling. And in fact, I didn't use this function, but Mathematica has a function called riffle. Okay. So this is just the link to the YouTube video I did before on this, and then the sort of PDF of my previous notebook. All right. So I'm going to do this different. So I took like the direct approach the last time, and then I made an array, or I made a list, I should say, and did the riffling, did the shuffling, did the perfect shuffling. And the problem is to sort of see for each size deck how many times you need to riffle it until it comes back to its original order. And I was taking a fairly direct approach by sort of creating the list and walking through all of them. So I'm just going to repeat that here. I have 20 cards. In my counting, I'm going to always have an even deck, so I will start counting. Sort of, this will be my sort of 10, I'll call it 10, even though it's like 20 cards in what I do later. I make an array of a list of cards. I make a copy of that. I say I haven't shuffled it yet. I'm going to make another array for the sort of shuffled array. And then while the new cards 2 is not the original, I'm going to keep doing the shuffling. So that the while loop is to keep riffling, shuffling until I get back to the original order, and the for loop here was the actual shuffling. And so then I've done a lot of printing here, but I said, here's on my first count, I had the cards 1 to 10 and 11 to 20. And, you can see that 1 and 20 always stay in place this time. But the 11 comes in and occupies position 2, and 2 moves to 3. Okay. And what I've done here is I was working, this is what I was doing before, working with the array and actually shuffling it. But what I'm going to start to do is follow the 2. So that the 2 started in position 2, and now it's moved to 3. And then the next time around, it's moved to position 5. Now it's now it's in the 3rd position, but now 2 things are going to be interleaved, so it's going to move to 5. Then there are going to be 4 things in front of it, so I'm going to add. So I add 1, then I add 2, then I add 4. So you'll but then at some point, so the numbers go up, sort of add 1, add 2, add 4, add 8. But then at some point, the numbers start to go down because you start to reach the end of the deck. So for a bigger deck, that little pattern would go on longer, but eventually it breaks down because of, that we sort of move into the second half of the deck. So, all right. So I'm going to look at these numbers, and this was just an arbitrary size. Now I'm going to just do something just purely with numbers. but these numbers are thought to represent the position of the two in the shuffled list. So now I'm using my notation of calling it 10, but I'm going to do something. Um, the max seems to be 2 to the num minus 2, and that is there are 2 times num positions, but the 1 never changes, and the 2 the first card and the last card never change. The 1 and the 20 never change above. So they're sort of uh, the possible locations. There are 2 times the number minus 2 sort of possible positions. Um, okay. But I'm going to go through, so I'm just making a for loop to go through all of them. Up here, this was, strictly speaking, a while to stop it. Um, but I'm doing a for loop, but I'm regaining the sort of functionality of a while by having an if inside my for loop with a break. So this is as high as I'm going to go, up to 2n minus 2. But if this thing I'm calling pause for position ends up equaling 2, then I'm going to break out. So that's the same effect as my while. And what am I doing in this loop? I'm incrementing my counter. S count is just the number of times I was in this loop before I leave. And I am taking my position. I'm adding a power of 2. So we saw that pattern up here. It was 2, and to get from 2 to 3, I added 1. Then to get to 3 to 5, I added 2. To get from 5 to 9, I added 4. To get to 9 to 17, I added 8. So I'm taking my previous position and I'm adding 2 to the I. That's the beginning of the pattern, and then it starts to mess up. What I'm claiming here is that the messing up is just a modulus of 2 times num minus 1. I'm going to print that out, and then again, if it's 2, I'm going to stop. And then at the end, so I'm printing, you'll see here the position of the 2, and then at the end, you'll see my count. Okay, and then you see I've already run it, but let me run it again, Shift Enter, and you see here 3, 5, 9 to be expected, 17 to be expected, 14, 8, 15, 14, 8, 15. Then let's look at the bottom, 7, 13, 6, 11, 2. 7, 13, 6, 11, 2. And it took 18 shuffles. It took 18 shuffles. So this seems to be capturing that the number of times we need to shuffle in order to get back to the same order without ever being without doing the actual list, without doing the actual shuffling. So it's sort of a more efficient way. So then I just decided to get sort of 1,000 of these. So with it being, did I hit Shift Enter? Shift Enter. There we go. So it's black, so it's thinking about it, but it did it, to do 1,000 of them with actual lists was going to probably overload Wolfram-Cloud, but here it spits it out relatively quickly. And in the previous example, I have that a list of numbers, and I haven't compared all the numbers, but I've compared a lot of the numbers, and they always seem to be the same. There is one, should point out, there was one odd thing up here. One of the positions was between 10 and 18, I have a 0. And between 10 and 18, I have a 19. So, and that's the sort of modulus thing. So up here, there is a 19th position that the card can be in, but when I'm just playing my modulus game, I get a 0. But all I really care about is that it's not 2. It's not the original position, and I carry on. So I mean, I could work with some if to correct that, but it's pretty unnecessary, I would say. Okay, so here is 1,000 results of how many times it took me to riffle to get back to the original order. Here is the plot, and you see these sort of lines, these lines, and they happen to have rational slopes. These ones have has a slope, I think, pretty much 2. There's one in here that is 1. This one might be 3/2 or something. So there are some sort of simple, nice. So if this was 800 and that was 4, so this is probably the 1. This is the 2. This is the 1. This might be 2/3 or something. But there are these nice rational fraction things where I'll call them solutions. These solutions line up. And I found some of these, the relationship between X and Y for these is fairly easy to figure out, but sort of what X's are on, what X's lead to solutions that lie on that line. That is harder, that I've not seen any pattern to. I've had more luck sort of figuring out the X's with the small ones. And I found 2 sort of low line patterns. And that was in the powers of 2 and one more than the power of 2. So here you see 8 gave you 4, and 16 gave you 5, and 32 gave you 6. So that was an easy pattern. And then one more than that, a 9 gave you 8, and 17 gave you 10. So one more than the power of 2 was also fairly simple. And those were both sort of logarithmic relationships. So I decided to look, since I had more luck there, I decided to look more at other smalls. Let me just remake that print. So I decided to pick out the smalls. I took out the ones that I've sort of already accounted for. So I'm looking through my results. I have this list of lists, or I'm going to call the inner ones tuples. So I have this list of tuples, and I said I wanted small ones, so I just sort of said keep it if it's less than 16. And then here were the 2 patterns before this. This is sort of the powers of 2 and one more than the power of 2s, and those were already sort of accounted for. So that relationship was logarithmic at base 2. So this is log base 2. So that's that power of 2. And so I pulled out the small ones that were not accounted for by my pattern using select. And then I just sort of made a plot of them, a list plot. But I also did the following. Given that it was like powers of 2 and powers of 2 plus 1, I decided to look at these in binary, in base 2, and to see if I can find any more small patterns. And I can do that with Mathematica's base form. So I'm going to, I selected out these numbers and called them small. So I'm looking for the ith small tuple, and 1 is the first value, what I call that X. And then I'm showing it in base 2. So I'm showing it in binary. And then I'm showing the actual number. So I'm okay with small numbers converting from binary to decimal in my head, but once they get a bit too big, but just to make the system do it for me and then show me the second number. So I'm just making a list and showing these things in binary to see if I see sort of some binary patterns going on, to sort of pick out a few more of these. And I found some. What I should do with them, I don't know, but it was just an exercise to keep me busy. So here are some patterns. I started up here with the first couple of patterns, writing them in powers of 2, which is effectively binary. And then down here, I just gave up and gave you the binary. But if it was 2 to the 3, 2 to the 1, and 1, 2 to the 5, 2 to the 3, 2 to the 2, 2 to the 1, sorry, 2 to the 3, 2 to the 1, plus 1 was 11, 2 to the 5, 2 to the 3, 2 to the 1, plus 1. So it's one more power, 2 to the 5, then one more power, 2 to the 7, one more power, 2 to the 9, and then the corresponding y's. So that's a nice pattern in the x's, and the y's were 6, 8, 10, 12. So that's sort of a fairly nice pattern in y's there. So, and that's only, and I'll show below where I go higher than that. Up above, I went to 1,000. Below, I go to like 4,000. So we could test this even further. Another possible pattern starts with 2 to the 2 plus 1, then 2 to the 5 plus, I added a 2 to the 5, then I added a 2 to the 8, then I added a 2 to the 11, and these were 6, 9, 12, 15. So another nice pattern, sort of powers, a binary pattern or pattern of powers of 2 pattern, and the a simple sort of relationship among the y's. Here was another pattern. It was a 4, 3, and a 2 on the end, a 6, 5, and a 2 on the end, an 8, 7, and a 2 on the end, a 10, and a 9. So I had these sort of, in binary 2 1s, 1, 1, 0 something. And so I was not adding to what I previously had, but there was a pattern in the binary. Two consecutive powers, and starting, the higher power was even, and then the next one down, and then a 2 on the end, and those y's had a pattern of 8, 12, 16, 20. Now I just sort of gave up and started doing it in binary. So here was a pattern of 1, 0, and then 3 1s, 1, 0, and 5 1s, 1, 0, and 7 1s, 1, 0, and 9 1s. And those y's were 12, 18, 24, 30. So I'm going up by 6s there. And here's a similar pattern, but this was 1, 0, and then an odd number of 1s. This was 1, 0, and then an even number of 1s. And those y's were 10, 14, 18, 22. So these are going up by 4s. Those are going up by 6s. And then down here, I didn't get anywhere much farther than that, but I just decided to pull out what was left and plot it. So I just sort of took my original list of smalls and things that were in my patterns above, I sort of eliminated. So these were the ones that sort of I haven't accounted for anyway yet, and plotted them. And also redid the binary expression. And it was just a way to sort of produce some patterns and sort of, I didn't find any more patterns, but this has been a successful way to sort of look for patterns for these low ones. Um, so it was a technique for looking for them. Here I'm just going, don't have to run it for you, but again, this method was of generating these numbers was much more efficient than the actual playing with the actual lists. And so I can get the next, 1,000, another 1,000, and another 1,000 pretty easily. Um, so I don't need to run that. It does take a little while, but not very long. Um, and so some of these patterns I had above, uh, some of these patterns I had above took me into the thousands, and then I did indeed test it. So this pattern took me up to sort of 3071. And so I did run it and test that one, and it did indeed sort of fit my pattern of add four. So that was the purpose of those. Down here, I just, again, has not been successful, but just to show, uh, to ask that this technique of looking at the binary was successful for the very low numbers. Can I do anything with the high numbers? So the sort of that upper bound was the number times 2 minus 1. These are the ones that sort of go through the two sort of goes through every position it could possibly have. It can't have the first. There were two end positions, but the first card never moves. The last card never moves. So there are two 2n minus 2 possible positions. And these are the ones where I was following the two took every position. So it didn't return to its position until it had sort of every other position that it could have other than the one, other than the 2n. Um, and so these were like what I call the upper bound. I don't have any proof of that, but seems reasonable and sort of what we're getting, at least simulationally, or it's not a simulation, but working out all these lower ones. Um, and then, okay, so there are these. And then I thought, well, I had some luck with the binary, so but there were a lot of them, and I didn't really see any pattern there. So, but it was at least worth a try because I had luck with the low numbers. I tried to see if I had luck with the high numbers. Maybe one of the maybe I'd have more luck with a line with a few fewer points, so that I could with fewer points maybe I could see a pattern. But at this stage, I have not done that. All right, so just more playing with this problem. I mentioned the riffle, which I didn't use but could have used, and sort of is a function that does this interleaving action that we're sort of talking about. Um, I used a break instead of a while. I don't think I've done anything with a break before. And I was writing the results using base form, writing them in binary. I don't think I've done anything like that before. Okay, that's what I wanted to show you with this one. Thanks for your attention.